bump into each other and interact. So this is a 3D boost mass simulation that was carried out by Hissing and Cathode. On the left there, so it's strictly periodic. So the eddy and the waves we separate with a normal mode decomposition. On the left there is the vorticity of the eddy, and on the right is the vertical velocity of the wave. So we have a fully evolved quantity-tropic flow, and we inject a plane wave into the flow. And what you'll see when I play this in a minute is that the flow has no sort of preferred direction. The propagation, the speed of that the rotation of the eddies is pretty much the same at the start and end of the simulation. And they're, yeah, basically the flow is unchanged by the wave, but the wave which has a preferred wavelength and direction, and it loses both of these things. So what this is indicative of wave scattering by large-scale eddies. So yeah, we're considering the limit here where the wave amplitudes are small, so the waves aren't having an effect on the eddy, but their energy is being scattered by the eddies. So you can model this with the 3D business equations. You can also use a simpler model like the rotating shallow water model. So this is a simple 2D model where we have this constant layer height, big H, and then the little h is wave perturbations to this, this background layer heights. We're assuming flat bottom for simplicity here, but you can include a topography if you want. So that's your rotating shallow water equations in the box there. U is the horizontal fluid velocity, and then there's some convection terms, some Coriolis term, and then it's balanced by a gradient in the variations in this layer height. And then there's also the CNC equation, mass conservation. So this system is useful for us because it can support both balanced eddies and also waves. So if we linearize this and look for wave-like solutions, the wave frequency is given by this expression in the box here. So there's some Coriolis parameter, G, H, the layer depth, and then K squared is the horizontal wave number. And why I'm drawing your attention to this is because if the horizontal wave number is constant, then the frequency of the waves is constant. And this means that in spectral space, in wave number space, the constant frequency surface is a circle, which you can see above the box there. And in a linear system, at least the eddy frequency is 0, so we have these slow eddies and these quick waves propagating on top. So ideally, we'd like to somehow describe how the wave energy is evolving in the nonlinear system. And to do that, we do a WKB ansatz. So what this means is that we split our flow velocity into an eddy component, big U, and then a wave component. So there is a wave amplitude U prime, and this evolves on the same scales as the flow in time and space. And then you have this quick phase e to the I theta, right? So that's sort of represented in the schematic at the bottom of the slide there. You have these quick oscillations, and then they're modulated with pairs to a real background field, which is the flow. And if you use this WKB ansatz in your rotating shallow water equations that I showed you before, you can show that the conserved quantity that we're concerned about is wave action. This is proportional to wave energy, so that's the A there, is proportional to wave energy. So we can solve this equation to find the energy distribution of the intervals. And yeah, I mean, it's not so much interesting algebra, but if you want to look at a rate action conservation derivation, you can look into this reference here, which is for the presentation system. And yeah, the other thing to point out here is that the total frequency of the waves now is the intrinsic frequency, so the frequency for the linear system, and then you have the U dot K, which is Doppler shift. So the frequency is being changed by the eddy in the background, and that's how the scattering interaction comes in our system. So we can solve this wave action conservation equation equivalently by ray tracing. So all this is you put a you initialize a packet constant action, and then you propagate it through, well, here we're propagating it through a stationary balance flow. So, yeah, the ray equations are equivalent set up to stationary that. So the point I'm trying to make here is that I'm sitting in a regime where on the left there, your blob of constant action, it's not really being refracted much. You'll see that when it's passing through these eddies, it does get refracted a little bit, but yeah, not so much. But then if you're in spectral space, so that's on the right there, and the blob of wave action is being distributed around this circle of constant frequency. So in the limit we consider, there's no, the only spread of energy is around this constant frequency circle. And maybe you can believe that in a long time over here, this is looking something like a diffusion process of energy in spectral space. That's because it is a diffusion process, and you can see this more clearly if we initialize loads of blobs of constant action around in a single place and let them evolve through this flow, which is what we do next. So, yeah, the energy all starts in one place, and then these rays sample the flow, and they get refracted out, and then they move around this constant frequency circle, and you can describe this as a diffusion in spectral space. So it's a diffusion like you see in a heat equation, or maybe some concentration of particles, but somewhat confusingly, it's happening in wave space. So it's describing how energy spreads across waves. So we can formulate this mathematically, which is what we do here. So, yeah, the starting point is wave action conservation, and then you make this assumption that the background flow is weak. And that corresponds to the fact that these constant action blobs weren't getting refracted so much in the flow. So if we make this assumption that the flow is weak, that amounts to putting an epsilon in front of u dot k. So our Doppler shift is weak in our wave frequency. And then we do a translation expansion of wave action. We make some other convenient assumptions that the eddy field is steady and homogeneous statistically. And after a few steps of manipulative probability, you reach a diffusion equation in spectral space. So that's on the top right there. On the left, you have the change in action, and then on the right, you have a diffusion. But you'll know that these gradients are with respect to k, the wave vector of the waves. So this is diffusion happening in spectral space. The components of this diffusivity are described by the integral there. You don't have to worry too much about the details, but it's coming from the Doppler shifter, and that's why you have these gradients in the flow. And it's an ensemble average of the gradients in the flow. And it turns out we can also write this as a function of the energy spectrum of the flow. So all you need to do to describe this diffusion process that I showed you in the previous slide is you need the energy spectrum of the flow, and then you can say statistically how the energy of the waves is developing. And for the slowly varying eddy, in case I showed you the stationary eddy, there's only one non-zero component to this diffusivity tensor, and that's the component that describes diffusion in the azimuthal direction, so that's around this circle. So that's why you only saw, on average, all the rays moving around this circle of constant frequency. So, yeah, this is not a new theory. It was first introduced by Wilson brothers in 1977. They did it in the context of wave-wave interactions, and they also mentioned it as interaction. And then I guess it's enjoyed a little bit of a resurgence recently through the work of Jacques and other members of this group. So the first paper that he published was with Hussein and Mars, my predecessor, and they were comparing analytical results from the diffusion equation with a 3D boost mass simulation similar to the one I showed you at the start of the presentation. So what we have here is the wave energy spectrum as a function of horizontal wave number. And the diffusion equation predicts that this is spectrum that goes like horizontal wave number to the -2. So you have this nice parallel, and indeed that's what you see from the boost mass simulation, which is the one. In this work, they assumed that the background eddy was so slowly evolving it could be considered stationary. And in the 2023 paper that we did together, we relax this assumption and allow there to be some time dependence in the eddy, which results in spreading across the constant frequency circles. So in 2D, this would be a spread across your circle. In 3D, it's a spread across the cone, like we're currently getting showed a day or two ago. So this is a cross-section of the cone cutting down the middle. You have vertical wave number and horizontal wave number, and you can see that energy mainly spreads up this cone, but there is some spread across the cone. So in the middle there, that's the BCMS simulation, and then on the right is our prediction. We found a nice analytical expression of how this energy spreads to the diffusion end. So yeah, qualitatively they agree. There's some differences. I encourage you to look at the paper to convince yourself that the prediction is relatively good. That's not the point of this talk, but the point is wave diffusion is useful to think. So this is all in 3D. In the 2D shallow water system that I've shown you already, this was examined by Oliver Bühler, Shaker Smith, initially ranging on, and then now there's a recent manuscript I think has been submitted to this, which is extending this stuff to 2D. And then, yeah, I'm collaborating at the moment. This is mainly the work of Gaspar Joffora at EWM, and he is looking at applying this in types, which for a number of reasons is difficult. But yeah, it was also relatively good. At the bottom there, you've got the prediction from the diffusion equation of spread around the circle and simulation of systems. So that's very much a work in progress, and hopefully the system can help to hear about it. Okay, so yeah, the point from this slide is wave diffusion is well studied and relatively useful. So as a summary process plot, you can describe these wave-eddy interactions with your direct numerical simulations. So either 2D shallow water or 3D BCMS, you get some nice scattering. If you want, you can invoke scale separation, then you get a simpler formulation, which is wave action plus station, and this is equivalent to ray tracing. So that's scale separation in space and time. And then if you further make this essentially in a weak eddy, then you get wave diffusion, which is on the right there. And this can be used for parameterizing wave energy in models, predicting analytic expressions for wave number frequency detection, purely from the eddy energy structure. So that's all well and good. But the Doppler shift is not the only inhomogeneity that the waves experience. So far, we assume that the intrinsic frequency of the waves is constant, and the only thing changing in the wave frequency is the eddy. But you know, in the BCMS system, you might have variable stratification. In the shallow water system, you have variable layout, and these things aren't accounted for so far. So what I'm going to address in the rest of this talk, pretty briefly, is accounting for other forms of inhomogeneities in the wave frequency. So as a start, we can extend the diffusion framework that I showed you a couple of slides before to include any sort of inhomogeneity in the wave frequency. So that's exactly what we do. Our starting point is always wave action oscillation, so we're always invoking this scale separation between the waves and the inhomogeneities. And our wave frequency now, instead of being an intrinsic frequency plus a Doppler shift term, is a constant part, this omega naught plus a inhomogeneous part, which is omega 1. And to reduce our diffusion equation, we have to assume that omega 1 is small, so we put this epsilon in front, and then we make the same assumptions we made on our background flow about omega 1. So it's large scale and it has homogeneous statistics. And then we do the same for the spatial expansion again, and we get the same looking diffusion equation, but this time the diffusivity answer is not just a function of your background flow, you have any inhomogeneities involved in this omega 1. So if you only have Doppler shift, this becomes the diffusion tensor flow, but you can also include other things which change the frequency. So I'm going to take you back to our example of rotating shallow water. And at the start in this lecture, I said the waves were propagating on top of a constant layer depth. In actual fact, if you have geotropic balance, which we do for eddies, the background height is being changed. So in the bottom right there, you see expression of geometry. We have the Coriolis force starts by this gradient here. background field. So necessarily the height is varying on the same scales as the flow velocity. And this introduces a changing component in the intrinsic frequency of the waves. And what I'm doing at the bottom there is just tailor expanding the intrinsic frequency so that we have a constant part, which is s squared plus gh on k squared, so that's our omega naught. And then you have a inhomogeneous part, which is your Doppler shift term plus a small perturbation due to this variation in light hours. So we can use this in our ray tracing. And yeah, maybe it's quite difficult to see the differences between the shift ray tracing and the ray tracing which includes both effects. So there's the nuance from the audience. So on the left we have Doppler shift, and on the right we include both effects. Maybe you can convince yourself that there's more refraction when you include both effects. And in the long time there, I think this does become apparent in spectral space. You get more diffusion around this circle of constant frequency, although at the moment it's not behaving and it doesn't look that way. Yeah, you can compensate as well. Yeah, so yeah, and also, I mean, each of these, this is a single iteration. You really need to do a lot of iterations to see how it changes statistically, which is what I'll show you in a couple of slides. But we modified the actual quantization equation, and then now we're going to revisit wavelength diffusion. So we have this perturbation to Doppler shift, the G delta H, and that introduces a new component in our diffusivity. So whereas before you just had a Doppler shift diffusivity, now you have one coming from height fluctuations. And that just comes from substituting our expression for omega 1 into the expression for the diffusivity dij. What's kind of cool about this is that you have an ensemble average over cross products of omega 1. So maybe you expect terms where you have Doppler shift and height fluctuation in, but yeah, you can show that the cross products here are actually it's uncoupled, they go to 0. So you just have Doppler shift contribution and contribution height fluctuation. You can relate this height fluctuation contribution to the eddy energy spectrum via the digital balance I showed before. Yeah, then through that we can relate the magnitude of this diffusivity. So that's what this plot here shows. So it's just the diffusivity computed for an energy spectrum of the shallow water simulation I showed you in the radiating simulations. And it's a plot against Berger number, and then as we vary Berger number, we also vary Roscoe numbers. So each of these three plots, each of the three crosses correspond to a different Roscoe number, and you have Berger number on the x-axis, and the diffusivity on the y-axis. So the red line is just height fluctuation effects, the green line is just Doppler shift effects, that's what I showed you at the start. Somehow this is all normalized so the Doppler shift is constant. That's just a convenient choice of scaling on the y-axis. And then both effects are given by the blue. But really the point I'm trying to make here is that, so for quasi-geostrophy, Berger number is order 1. And this height fluctuation effect is not ridiculously small, it's like a quarter. So that's still a similar order of magnitude to the Doppler shift. And as you move to smaller Berger numbers, so planetary geostrophy, the height fluctuation effect becomes the same order of magnitude or even more important than Doppler shift. So in diffusion, this is something that in the 2D case you should be considering. Or at least you should check whether it's small. So this is exactly the equivalent plot to the many rays I showed you before. So it turns out that we can predict the value of this diffusivity tensor using the deviation of the rays from their initial angle. So that's why I'm initializing all sorts of angles. All I'm keeping track of here is how their angle deviates, and then yeah, there's a nice close form expression that gives you d5 which I've entered here. But yeah, so from this ray simulation, we somehow estimate the diffusivity, and it's a reasonable estimation. There's a little bit of a period at the start where it has a wind up until you get better approximation. And the reason for that is in the asymptotic, we approximate an interval from 0 to t to 0 to infinity. So there's a little bit of time before your assumption is valid. And what you can see here is that the magnitude of this phi phi, the height of the Doppler shift distance. So it can be an important effect. So yeah, we've done this for shallow water. You can also do this with 3D mass.
The neckline smaller than the other. Those effects are smaller.
Yeah, sorry, maybe it's proportional to negative the diffusivity tensor. Something like this. Yeah, it's larger. Yeah, the actual expressions. I think this is a negative quantity. I think this plot would benefit from some axes actually. So yeah, maybe in the future you'll see this with some axes. I mean, it's an improvement on the last time I showed it. Before I did have the exact solution, I didn't even say what it was. So in a way, yeah, maybe the way that it is in 2028, you'll see some plot. Who knows? Maybe I'll be presenting some new work. Yeah. Okay. Maybe I'll leave some time for questions and skip through the business stuff. So there's an equivalent where in the pipe fluctuation, you're inducing changes to, in shallow water, you're inducing changes to the background pipe. In the business system through the thermal wind paths, you're inducing fluctuations in the buoyancy field. And we find that for the business system, this is less of a significant effect. I'm happy to answer questions about that if you want. Yeah, you can also describe topographic scattering through exactly the same thing, but just instead of the delta H1 being due to geometry, you have a delta H2 as well, which is due to some topography. And I'll leave you with a summary. So you start with your Doppler equations, and then you invoke scale separation between your waves and your inhomogeneities. This gives you wave action conservation. And then for any weak inhomogeneity, which is the novelty of this talk, you can get a general wave diffusion. That's summarized in this paper below. Yeah, happy to answer any questions. Thanks very much.